Uh, okay. Thanks for the introduction. Yeah. First, I want to introduce myself. I'm Shibo Hao, and I'm a second-year PhD student at UC San Diego. I work on everything around learning model, specifically the reasoning ability or planning, and this tool using work like ToolkenGPT. So yeah, today I'm happy to share our work in New Year's 2023. So yeah, the title is ToolkenGPT, Augmenting Frozen Language Models with Massive Tools via Tool Embeddings. Okay. For the past year, I think everyone has been impressed by the capabilities of large language models. However, if we really want the LLM to assist people on some real-world complex task, we find it's still missing some important abilities like this one. So the user is asking the LLM to purchase a laptop when there is a certain discount. And unfortunately, this case requires some abilities that even the strongest pre-trained LLM don't have. For example, to solve this, to respond to this query, the LLM needs to do accurate calculations, have the access to the real-time word knowledge, and have the abilities to take real-world actions. A very promising idea to extend the abilities of LLMs is to augment them with external tools, like using a calculator, connecting to a database or APIs, robotic actions, just like how human makes use of the tools for some difficult tasks. Uh, ideally, to this user query, an LLM should be able to respond perfectly with the help of a bunch of tools. Okay, now I'm going to introduce some previous work about tool learning. So there are actually two major paradigms to teach LLMs to use tools. And first, we can fine-tune the LLM if we have some demonstration of tool calling as the training data. So yeah, just like the figure. However, fine-tuning LLMs can be really expensive, and every time the toolset is updated, you need to retrain the LLM, which exacerbates the problem. An alternative method is in-context learning, so which is directly prompts LLMs to follow the tool using demonstration in the context. However, LLM can only learn from the text description of a tool or only limited training samples in the context, which leads to very shallow understandings of tools. And when there is a very large tool set, it's even more challenging for LLMs to learn every single tool from just one context window. To motivate to overcome all those limitations of previous methods, we propose a new tool learning algorithm called ToolkenGPT. Okay. Okay. So yeah, first let's go through some background. We can recall how a standard LLM predicts the next token. Okay. So given a question, is there a question in the chat? Oh, okay. Yeah. So given a question, let's say the LLM is trying to answer the question step by step and by generating the next token, and say we are arriving at here and trying to predict the next token. So, um, so based on the hidden state of large language model and the token embedding layer, actually there's a metric multiplication, and after the softmax, we'll get a distribution of the next token. However, yeah, as we just talked, LLM is not good at math calculation, right? So here the next token should be a number resulted from a calculation, and it might not be a good idea to directly predict the token in this way. And here comes the main idea of ToolkenGPT. if we have the embeddings of tools, we can actually predict the tool call in the same way as predicting the next word token, and that makes the word token. Okay, so now first let's assume we've already got those token embeddings. Um, we'll show how to train them later, and now we can just append them to the language model head like this. So basically, if the embeddings are good enough, the LM will predict the square token at this step because that's what needed for the calculation. And then the next step is to complete the argument. So the LM will jump into another context, which we call tool mode. And here we provide a few demonstrations of the selected tool in the context. And also, if everything goes well, the LM can correctly predict the 60 as the argument. And finally, the call is executed and the result is sent back to the reasoning mode. So basically, that's the inference process of TokenGPT. Okay, then yeah, we can move forward to talk about the training of token embeddings. The objective of training is basically similar to standard language modeling, but here different from the input sequence S, which is composed of word tokens. We also have a target sequence S prime labeled with two calls. So at each time step, the LM is conditioned on the input sequence S and trained to predict the next token or token in the target sequence S prime. So regarding to the training data, if we have the data set labeled with two calls, we can easily transform it to these two sequences. Or if we don't have two calls annotations, we can also synthesize some training data by prompting LMs to generate more data labeled with two calls, which is quite similar to self-instruct methods. It's also kind of like the data generation method in Toolformer. Yeah, so basically the data can be from both human annotation or synthesized by language model itself. Okay, and then let's take a closer look at what's happening during a training step. So at the beginning, we'll randomly initialize the embeddings for some tools and append them to the language model head. And yeah, as we mentioned, so only these new token embeddings are initialized from scratch, and all the other parameters are kept frozen, which are the same as what the language models have at the first place. And we'll calculate the next token distribution with forward pass, at each every time we want to predict the next token, and that's the forward computation. And then compared with the next token in the target sequence S prime, which is a label, we are able to compute the loss and backpropagate it. So in this step, only the token embeddings are updated, which will all the parameters of LMs, including its word tokens and other layers, are kept frozen. So that actually leads to a very good feature. The first one is that the information of the tools is only trained in their own embeddings. And yeah, basically their representation are disentangled from each other and all other knowledge inside large language model. In this way, we can add, move, remove, or update a tool without impacting other tools or the knowledge inside LLM. And yeah, the second point is the backpropagation will not go through the main body of LLM. So it will just stop at the top layer of LLM, which means the training can be really efficient both memory efficient and time efficient. And essentially, the bottleneck is the forward path in the LM. So basically, to train the token embeddings, uh, the time and memory it cost is just the same as doing inference with language model. Okay, so yeah, here comes the experiment. We equipped Llama models type of tools, math, knowledge base, and robotic actions. So for mathematical problems, TokenGPT is equipped with a few math operators. And here's a quick review of how the solution is generated. It's the same example we've seen a few slides ago. Okay, and yeah, that's the end. And in three different datasets, TokenGPT outperforms strong tool learning baselines, especially on the FunQA dataset, where the language model needs to call some more complex math tools. And our framework even helps Llama 33 billion model to beat GPT 3.5 on those math problems. And for knowledge-based question answering, we connect Llama models with knowledge base. So in this example, the user is asking about the winner of the sport event. Instead of directly generating the answer, TokenGPT calls the tool from a knowledge base to provide a more reliable response. And yeah, here's the run example. So in our experiment, we found TokenGPT trained with only synthetic data beats old baselines, and it scales well to over 200 tools. And the third domain is embodied plan generation, where the task is to generate a sequence of instruction that can be executable for an embodied agent, given a high-level goal. So yeah, if we directly prompt the language model with some in-context learning examples, as done in some baselines, apparently there will be some problems, like for example, uh, it may generate some invalid objects or actions that cannot be recognized by the agent or the robot, or it can also misunderstand the meaning of an action and thus produce some illegal instructions. So basically, in this case, sit means sit sit on. So this sit dex instruction doesn't really make sense. But that's something we cannot tell from just looking at the text description from the tool, right? And that's why we need to encode the tools into embeddings, which can capture richer information about the tool. So yeah, if the plan is generated with TokenGPT, these tools, first, we can put all the valid actions and objects in the token vocabulary, which naturally solves the first problem. And yeah, as I just said, since we can train the token embeddings with demonstration data, which help language model to understand its semantics instead of just looking at the text, it will have a better understanding of the tools that have higher success rate. And let me check the chat. Okay. Right. So for math-based problem, another technique is write a program to solve this problem. Yeah, I think that's a good question. So I think in this paper, our scope is to basically connect the language model with all kind of tools. And I would say writing a program and using a code interpreter is one of the many tools you can use, right? So imagine you are solving a very complex problem, and sometimes you need a calculation, and yeah, instead of the those basic operators like what I've just showed, the addition, multiplication, something like that. You can also treat the program or the interpreter, Python interpreter as the tool. So yeah, I guess the high level idea of our work is compatible with this kind of works using program to solve math problem. Yeah, I hope that answers your question. Okay. Um, yeah, basically, equipped with TokenGPT, the language model can generate uh, plans with better successful rate and also the grounding rate. Yeah, because they won't generate any invalid actions and objects. Okay. Back to how freezing and unfreezing the layers of TokenGPT works. Yeah, that page.
Yeah, if I could jump in, I think from the paper, just if you could explain that you're really just training this unembedding matrix. I think it was a WT, and that it doesn't really require you touching the regular vocabulary unembedding. So if you could just
Mhm.
kind of go over that part, then I think it'll be clear that you don't need to actually do any backprop, any training on the main model.
Mhm.
My question is it the last layer of the LLM which is being uh, trained? Like it's kind of a transfer learning?
Uh, sorry, I didn't get the question.
So when you're using the I think you're freezing the LLM layers, but probably the second last or the last layer of the LLM, you are pretty much unfreezing that, right? Is that true?
No, I think all the parameters in LMs are frozen, and
Okay.
we only train the token embeddings, which are introduced by us. So this parameter don't exist in the original large language model. We just initialize some parameters and append them to the last embedding layer of language models.
Okay. And those token embeddings are just one layer after the LLM, right?
Uh, I wouldn't say it's another layer. Basically, we are concatenate these two embeddings to the token embeddings. Yeah, so basically it's like expanding the vocabulary of the language model. But
Okay, got it. Okay,
yeah, okay, yeah,
thanks.
all right. Yeah, I think we can directly jump to the conclusion. Mm, all right. Okay, so the takeaway idea of TokenGPT is we can embed tools as tokens. And this method enjoys several advantages over previous methods and is shown to be effective on diverse domains. And some of the future work includes to plan for multi-step tool using, maybe uh, to solve a complex problem, you cannot rely on just one tool call. Like the case in knowledge-based question answering, you can simply call the knowledge base and get some knowledge to answer the user query. But instead, you have to plan for the trajectory of tool using and also the reasoning. So I believe that's something still worth exploring. Yeah, I'll check the question. Okay, the first question is that is there a practical limit to how many tools you can add? I think okay, so for the architecture, I don't think there's a limit of the number of tools. But if the tools are indeed too many, the language model can get confused when which tools to choose because yeah, just like a classification problem. So if you have many classes, sometimes yeah, it can be tricky to do that. And in our experiment, we found yeah, that's something very specific to the task. Like in our experiments of knowledge-based question answering, we can connect language model with like over 200 knowledge-based relation as tools. So yeah, at least it works in that domain. But yeah, maybe for some more um, uh, for some other domains where the difference of tools are really tricky, yeah, maybe that will be harder for language model to choose the correct one. Yeah. And for the comparison to former, uh, yeah, I think the main difference is that they um, they are one of the uh, fine-tuning methods I mentioned in the previous work. Let me find that slide. Oh, yeah. So basically, the first problem is that it's expensive to fine-tune the language model. Yeah, and especially for two former in which they did kind of pre-training scale of the training. They basically filtered a corpus, a very large scale corpus to do the training. And another fundamental problem is that this kind of fine-tuning method doesn't uh, scale to new tools. Like if we have trained the two formers, which take a lot of computational resource, the tools can be updated, right? Or sometimes the tools are just deprecated. We don't want it anymore, or we need some new tools. So once this change happens, do we want to retrain the whole model from scratch? Uh, yeah, basically, I think that can be very hard to scale up. But for TokenGPT, it's kind of we don't have these worries. Yeah, because the knowledge of different tools are disentangled, which means if you don't want any tools, you just unplug the token embeddings from the tab. If you want a new one, you just train a new one and append this new one to the vocabulary tab. So everything is flexible, and I think that's fundamental difference compared to the fine-tuning method. Okay, the next question is which normal vocabulary words are nearest neighbors to the embedded tools? Do all math-like tools get embedded? Okay, yeah, I think that's a very interesting question. We actually haven't done this experiment, but yeah, but my guess is that um, the tools used for different domain will be clustered uh, separately. Yeah, but just my guess because yeah, we haven't done that, but it's a good idea. And we use token to strengthen the inference capability of large language models. I'm not sure what this question means, but yeah, I think if we can have the embeddings of tokens, the language model can sometimes generate more reliable answers by calling the tools when necessary instead of maybe if you ask the language model to respond to some really challenging task, it may hallucinate. But hopefully with the help of tools, it can generate better response. Does that answer your question? Sorry, I'm not quite sure about what you mean by inference capability. LM with RAG only generates output based on the text similarity, but no inference. Do you mean the retrieval process? Like you only embed those maybe the documents with text embedding and do the retrieval? Mhm. Yeah. So I think that can be one advantage of ToolkenGPT because the embeddings of tools actually they encode deeper semantics of these tools by learning from the use case instead of just the text embedding. So yeah, maybe this example I mentioned is relevant. So yeah, basically in this case, it may appear reasonable to predict seat depth at this step, but you actually cannot determine is that a good instruction just based on the surface text. You only need to experiment with the environment and say, okay, this seat actually means sit on. So you should sit on the chair instead of sit on the desk. So that's something we cannot observe from the text. Yeah, I believe this might be a poor example, but for real world applications, I think there's indeed some information that cannot be inferred, but from just the text, you need more information source to embed the tools and or embed the relevant document if you were talking about a RAG in the retrieval scenario. So yeah, I think that's why embedding the tools as tokens is the most important takeaway we want to highlight because uh, we think in the future maybe we can also embed more information in the vectors like I don't know like now we are only using the data demonstration but in the future maybe there can be more source of data like text is one thing we can learn from and demonstrations and maybe uh, other informations. If you have tools that have some domain overlap, then their logics won't be normalized. If the tokens are trained separately, it's easy to remove or like adding. Yeah, I think that's a very good question.
Yeah, I can sort of explain that a little bit more. So like I'm imagining you have some very popular LLM like ChatGPT, right? and let's say you have 100 different organizations all, offering toolkins, but maybe there's some overlap because one is a simple calculator, one's a scientific calculator, one whatever, does algebra, one does calculus. It's a lot harder now to decide which tool to use. And it might be okay, like you don't have to necessarily pick the exact right tool all the time, right?
Mhm.
But
Mhm.
if everybody trains their toolkins separately, then they'll kind of all say, oh, it's a math problem, pick me, pick me. But whether, one of them is 0.31, one is 0.35, like you won't necessarily, right? But if you train them jointly, then you would see that separation, like, oh, this is a more scientific problem. I should use the scientific calculator because it has logs. This is a basic problem. Maybe I'm better using this or whatever.
Mhm.
So like when you did the question answering, right? You had all 243 whatever, predicates, but you trained them jointly. If one person had
Yeah,
trained
yeah.
100 of them and a different person trained 100 of them, then it might not have chosen. Does that make sense what I'm asking?
Yeah, yeah. I think, yeah, that's a very interesting question. Yeah. Actually, we haven't considered this problem, but yeah, it's
Yeah.
definitely a reasonable question.
Yeah,
Mhm.
because I think even if you do the joint training, it might turn out based on some of the data you have that it's still cheaper than fine
Yeah,
tuning,
yeah.
but it's just not quite as easy as plug and play, maybe.
Hmm. Hmm. Okay, yeah, that makes sense. Yeah.
Thanks.
So, yeah, I'm thinking maybe in the training, if we can add some negative samples, like instead of just the domain you expect the tools to work on, that may teach the embeddings, like in which scenario you don't really want to call these tools, and I hope that may, create more distinctions between the tools when it's not quite their domains. Yeah, but yeah, thanks for the good question. Okay, let me check other question. Continue. I think that this question depends on the capabilities of large language model. I believe GPT-4 can correctly answer this question, but yeah, maybe for Llama or smaller model, you may have difficulty in answer these questions. Yeah, you can prompt it to ChatGPT and see how it responds. I guess you can successfully answer the question. Yeah. Okay. Uh, yeah. So about the idea of embedding tools as tokens. Oh, sorry. No. Yeah, about the future work, planning for a multi-step tool using to solve more complex tasks. Yeah, I'll go back to the questions later. And we actually have some relevant works. This paper called Reasoning with Language Model is planning with a word model. And we also have a library, LM Reasoner, which is based on the formulation. And yeah, we kind of regard the reasoning problem as a planning problem. So you, in a sense, you are searching for the optimal sequence of reasoning steps to arrive at the final answer. Just like maybe the mathematical problem in our examples in the slides a few pages earlier. Yeah, so basically you may have different paths to reason over the question and give a final answer. So yeah, it's worth exploring like which components are most important in this process of search. Okay, and Also, I think since we have this framework of embedding tools, it's also interesting to see can we embed stronger tools instead of those maybe basic operators or knowledge-based relation or something like that. Yeah, actually, this idea has been applied to not necessarily applied, but we have seen some similar ideas on other domains, like this RT2 by DeepMind, which is robotic control large models. So yeah, basically they also have the special tokens to have the language model to generate actions. And yeah, maybe we also have seen other works in multimodal language model like this one. So if we want the language model to generate an image, sometimes we can generate here they call it string token, so that the model switch from text mode to the image mode and do some diffusion, get the image. Yeah, I think that's also another very active research field, which is quite exciting these days. Yeah, I think that's all about TokenGPT. Okay, I can answer other questions. What causes this TokenGPT to be overtrained? I'm not sure what overtrained means, but yeah, I guess one solution I just mentioned, maybe to add some negative samples can help. And can we add adversarial training to this? Yes, adversarial training. Okay. Yeah, that sounds promising, but I don't have a concrete idea in my mind right now. But yeah, it's a good question and suggestion. Yeah.
Yeah, Ravi, do you want to clarify that question? Are you thinking like a discriminator on choosing toolkins? Maybe? Is that what you mean by like an
So,
adversarial?
so I was thinking like, where you give a slightly different input, but, as you said, a lot of different groups can train it and it will give different parameters or different answers. Whereas what I mean to say is that it should not happen that, it's very sensitive to input. It should give the same output with slightly different input. So that's the kind of thing where it should generalize well. So that was my whole idea about like, can we add some perturbations or, kind of that things to make it more generalizable.
Mhm. Yeah. Yeah, I think that should be helpful. Yeah, good idea.
But I
Mm.
think the negative training idea is also good. If there is something, Shiva, can you point to it? Is there any resource for that?
Uh, mm, yeah, I cannot think of a concrete word right now. Yeah.
Okay.
Okay. Yeah. By the way, yeah, I actually have an appointment at 1 p.m., so I may need to uh stop at here. Yeah, thanks for the opportunity to present my work and the great discussion we had. That is, it was really great. Yeah.
All right. Thanks so much for joining us, Shibo. Hard on Zoom to do proper applause, but a few people are trying. So appreciate your time, and I hope you enjoy the rest of your weekend.
Yeah, you too. Thank you.
Thanks. So for me, I think he did mention this, but one thing that's interesting is that this idea of having special tokens, in his case, it's toolkins because they weren't really thought of at the time that the original model was trained, right? Versus something like RT2, whatever, they were like planned in from the beginning, right? But this is really kind of orthogonal to anything else you're doing. So you can do chain of thought, you can do tree of thought, you can do whatever, you know, you can still have your llama index or your lang chain workflow, but still potentially augment the power of whatever your base LLM is with some number of these augmented toolkins. And they don't have to be tools that the original authors. So if you're saying, I want to use Mixtral, but they didn't think about having a code interpreter solve more complex problems, I'll just have this toolkin that like identifies, hey, this looks like a situation where it'd be great to switch modes, write some code, and then drop in, you know, that information. The other thing that I was thinking that this paper didn't do is it seems like the tools are supposed to output something directly. And I was thinking another thing you could do is you can have a tool whose job solely is to insert stuff into the context. Like, hey, by the way, 6 times 8 is, what is 6 times 8? 48, right? It's not outputting 48. It's just saying in the context, if you need it, 6 times 8 is 48, right? If you need it, the, you know, GCD of 6 and 8 is 2, whatever, right? So then maybe you can like kind of blend tools where they don't have to be perfect at outputting, but they could just be like the sort of advisor whispering in your ear into your context. I didn't get to ask him about that, but I think just the general idea of having a toolkin, I think it's interesting because it's orthogonal. It's not mutually exclusive. Like, am I going to do toolkin or am I going to do something else? So I don't know if any of you guys had any other comments or question about this before we move on.
I joined like a few minutes right after you started, guys. Really great presentation. My question is, the way that you teach this LLM to use this tool is in terms of context, right? You give it several examples, like in the area of garden was the greatest common denominator and all that. You touched a little bit upon it in terms of what if these tools and their embeddings get a little bit dense in this higher embedding space. But that's not how we learn to use a tool, right? We have definitions for tool, like this tool does this problem, takes this input, gives you this output. So I imagine there will be a lot of input prompts that this won't be embedded properly, or this tool won't have the ability to identify that. Another way of finding GCD is by rephrasing your question.
Yeah, I think it's a good question, George. I would say this is like the first paper, so you could even imagine that you have a multi-level thing, so that just like when you're doing inference, if you want like something more creative, you could do like top K sampling, right? So you could say, I'm going to randomly select amongst the top 3 tokens, right? Maybe you have some meta algorithm that says, I'm going to look to see if one of the toolkins is in the top 3. And if so, I'm going to go into some kind of decision mode to like vet, do I really want to use this toolkin, or maybe I don't? It's not the right situation. Is that kind of along the lines of what you're thinking? Like, it wasn't what you asked, but I'm thinking that, like, again, it's orthogonal. You really could layer in other kinds of processes to try to like really decide, is this the right time to use this?
Yeah. To me, the question boils down to what is the decision making of which tool you use. Like, it's not explicit here. Like in the agent world, you have a coordinator. Oh, you want Python? Here's my Python agent. Oh, you want stats? Here's my stats agent. But that specific entity does the decision and reasoning for you. Here, it's kind of embedded in the language itself.
Well, in the paper, what happens is you just train. So like, let's say your word vocabulary is 50,000. Okay. So when you embed words, you have this 50,000 by Model D matrix that does the embedding. But when you do the unembedding, if you have 200 tools, then you have Model D by 50,200 matrix. So it's going to actually have 200 extra logits. And it's just basically saying that if your calculator logit is the biggest one, then instead of outputting the word that is, so, you know, the word or token that's associated with the max logit, we're going to go into tool mode for that particular tool. And in tool mode, what it does, he didn't say a lot about it, but it then takes your pre-trained prompt that's few shot, that gives examples of how to use this tool. So you combine your word context with the tool prompt that says this is the right way to use this calculator. And then it does an autocomplete on, it does a completion, you know, on that particular tool. And then it takes that and sticks it back in and then goes back into regular inference mode. I don't know if
Yeah.
that helps clarify.
No, that was helpful. Did
Yeah.
did any tool actually run, or is it just logit? And that's where the discussion ended.
Yeah, so basically it's just, so like for the question answering, they had, again, I think it was 243 predicates. So they trained 243 things like winner of, is a kind of, right? Whatever all those different things are, you know, is the capital of, you know, they trained 243 of those different things. And each one of those would only fire for specific language contexts.
Thank you.
So I was impressed that seemed to work pretty well. But then my question was kind of like, well, but what if somebody else trains another tool? Unless they're all trained simultaneously, then potentially you don't necessarily pick. You will pick a tool that matches, but you won't necessarily pick the best tool. Was what I was thinking.
I think kind of one of the critical pieces here is like LLMs can actually use some tools already. If you just prompt it and you say, here's your list of 10 things, here's how you call this function, and then it will just sometimes be able to do that, but it probably won't be that reliable. But then there's also kind of a hard limit on how many tools can you actually do, because your prompt's going to get a mile long eventually. And so this is kind of an interesting way of working around that a little bit and getting much better accuracy out of it, because you're actually teaching it to use it rather than just hoping that it understands the context and the pieces.
Yeah, you're teaching it to use it, and teaching it to use any one tool in isolation is very cheap, because all you're teaching it is what logit should I output given various text. So you're, the only thing you're training is that unembedding vector. The entire rest of the model's frozen. So
I think your idea earlier about actually having the tool execute and then having that become part of the context, I think that's really interesting, but I was thinking about it in terms of training, and I think that that would be difficult to implement potentially, because if you have something else that's substituting in a value, partially like you're reliant on the other tools to execute, and that's probably going to slow things down, but then you're also substituting something in, and that might screw up gradients and everything else. But yeah, interesting idea.
Yeah, I think yeah, it might require a little tinkering, but there definitely are like whatever, like LangChain workflows where you do something and it doesn't actually directly output, it's just putting more context.
Yeah.
Making more context available for you. But yes, maybe it does require more of a loop in order to know what to do with that extra output from the tool, you know. And who knows, maybe it would slow it down if you have too many of these, but it's sort of like, you know, you talk about blah, 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 you talk about, you know, California, and then it can just say like, hey, by the way, the capital of California is Sacramento. And you could just decide, I'm not going to use that. Like, tool, you were right that that's the correct capital, but I, as a language model, am deciding that that wasn't really what the user was asking. So I'm just going to continue with my normal completion. Any other comments or questions? All right, great. Thanks everyone for joining us today. Maya, would you like to share the topic that you shared with me, or would you rather push it to future session?
Oh, I'm fine to talk about it now. You think it can fit in?
Yeah, I mean we're kind of at the top of the hour, but I think from the preview I got, it's not very long. So I think what we'll do is my proposed a lightning talk. So we'll do this, take like 5-ish, 10 minutes, you know. And then we do have the office hours scheduled. So then Ryan and I happen to take whatever queer programming Kaggle questions right after Maya goes.
Okay.
All right, go ahead, Maya. Thanks. You should be able to share your screen.
Yes, I'm looking. Okay. Okay. So it came after my investigation for one of the Kaggle competitions. You know, that idea that you can look at the Kaggle competition, which is almost, which is solved or almost solved, and study something and learn something from it. So I look at this competition, Google Isolated Sign Language Recognition. And what the data they were providing is points. They said that they already tried convolutional neural network on images and it wasn't working good enough for them. So they derived all significant points. For example, this set of points, it meant a hand outline. So we were given X, Y, and actually Z coordinates too, but the thing is that the coordinates weren't very reliable because I tried to plot lengths of the of the forearm with respect to the I forget how it is called. Okay, the lower part of the arm and the upper part of the arm, I plotted them against each other and I discovered that their lengths by their data have negative correlation. So, which is apparently not quite true. I was doing it because I thought to use this information for data manipulation, data augmentation. Okay, so let's talk about convolutional neural networks, how we can use them in such case. And the problem with convolutional neural networks is that, for example, if you have 2x2 filter, then what you can detect is horizontal and vertical lines. And some lines which are not quite horizontal and vertical, kind of diagonal. It is not very useful in this particular case because we have rather complicated constructions. We can use bigger filters, but we do not have good angle discerning here anyway. So let's talk how we actually can recognize angles on a plane. Just in case, you know, mathematical education goes in stages, and sometimes they study one thing all everywhere, and sometimes they decide that it is not good for math education. And I mean in schools, sorry. And sometimes they think that should be adapted, and they study another thing. For example, I happen to be in the stage where they study a lot of geometry. We studied plane geometry, we studied 3D geometry, we studied trigonometry, we studied on unit circle, and such and such. And I know that afterwards it was decided that it's too complicated for too many kids, and they changed it. And for example, they do not study 3D geometry anymore. Plus, I know that students whom I taught in colleges, they do not know unit circle well, so I guess they do not study it much anymore as well, because we spent a year on it. Anyway, if you have questions, please ask, because it could be that I rely on something which, and you were deprived from it. Okay, unit circle. Unit circle is very convenient because we consider triangles which always has hypotenuse equals 1, which mean that projections to x-axis and y-axis are exactly cosine and sine. Any questions about it? Okay. Anyway, if you still need to know something about it, please ask. So our angles are inverse trigonometric functions. Arc sine of x, I don't know how it was in your school, or inverse sine, or arc cosine of x, or inverse cosine. There are two types of notations. So what we need here is how we can restore the angles from coordinates. And here I took 1,000 points, split them in usual test, trained and test subsets. 70% were for train, 30 for test. And the blue line is the true line. So this is the x values plotted against exactly the inverse trigonometric function values. And I took number of layers, which is usually advisable. We take a size of a layer, which is about half of all points which we feed to the network. So, and I tried with 1 layer, with 2 layers, with 4 layers. What do we see here? We see that the singularities for these functions, the functions have singularities at endpoints. We have a bit of a problem. And singularities are the kind when we have vertical tangent line. Vertical tangent line means that derivatives near these points goes to infinity. And basically there is no way to fix it, because this is a functions. We have exploding gradients here. We can look at cosine, we can look at inverse sine. It is the same problem here. And let's talk about how the functions are usually computed. So I did a list of bottlenecks for inverse trigonometric function calculations. First, you see again the vertical tangent lines. Second, how they usually computed on your calculators and your computers. Calculators often use estimation methods. There is its name, CORDIC, and the thing with it that at each step we need to adjust our calculation algorithm, which means that it is not very simple to compute these functions. What is usually done with computers is, because computers have huge memories compared to with calculators, then they just keep lookup tables. And intermediate values, because values they have in lookup tables are interpolated. And even some calculators, if they have enough memory, they use it because it is much quicker and reliable. So, and for this particular case, there is another problem for inverse functions, because we do not start with normal vectors, which means that we need to divide by a distance. And this operation has its own singularity. It has a vertical asymptote at 0, which means if you need to scale your data, then you should be careful with the scaling. You can introduce a lot of noise. Going back to the Kaggle competition, which I considered, they have a pause and pause points. And the problem with the pause is that you actually need to cut it off, because one of the most crucial gestures is pointing to a chin, to mouth, to nose, and to eyes, and to ears. So this kind of points and how a finger is placed next to them is very important. So this is about scaling. And in the Kaggle competition, people use transformers to coordinates. And they had restriction on memory and time. So with 250 classes, the best accuracy was 90%. I mentioned about the restrictions because I look at it and thought, why? There are a lot of angles. I can compute all the angles. And I did. I computed how many? The number of points you need for this whole thing is below 100. I mean, they give more points, but when you need what is actually meaningful, here it's less than 100. The number of angles I compute was about 3,000. And my model didn't come through, wasn't accepted at all, because for each record, it was about a minute of computations for all the angles. Okay. Okay. So my conclusions here is that for a picture with a lot of crucial angles, you'd better use point coordinates. And well, apparently more complex neural network structures are likely to yield better result. And be careful with scaling. That's it. Thank you for your attention. Any questions? If there were any questions, by the way, I don't see them because they're on another of my screens.
Thanks, Maya. Thanks for sharing. I feel like one thing I can generalize from this, right? So like inverse trig functions are generally defined over a range of like, pi, right? So like our cosine, maybe it's 0 to pi, our sine, it's, negative pi over 2 to positive pi over 2 or something like that, right? So anytime your data is on a limited range, you need to think about I think the lesson is like think carefully about it, because the neural network generally is just going to be from negative infinity to positive infinity. So you see, where for certain problems people use sigmoid or they use whatever, but like I think that's just sort of like the broader lesson from what you're talking about, because yeah, you're getting bad predictions near those vertical asymptotes, right, Maya? Cool. All right, thanks. I think we'll stop the recording here, stop the formal part of the presentation.